March 17th, 1944. Normandy Tank Depot, 3 kilometers behind Utah Beach. The sounds were not those of refined engineering laboratories or military boardrooms. They were the sounds of arc torches, hammers, diesel engines, and men arguing over measurements drawn in chalk on steel. A Sherman M4A3 rumbled past the inspection shed, its olive drab armor broken by curious angular slabs welded across its hull, unofficial, unauthorized, and certainly illegal. The modifications were crude in appearance, but their placement was deliberate, specifically at 47-degree angles, measured and remeasured by Master Sergeant Frank Kowalski. He was 32 years old, born in Detroit, raised on factory grit and industrial noise. He had never sat in a university's classroom, never studied metallurgy, never opened a textbook on ballistic theory, but he had spent 15 years watching metal behave, under pressure, under weight, under heat, under collision. He had welded fenders for Buicks, chassis frames for Chevrolet trucks, and experimental plating for early industrial machines. He had learned, not from theory, but from sparks, sweat, and steel. He understood something the engineers in Washington often forgot, that steel had behavior, not just properties. You didn't just measure it, you lived with it. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Army regulations were clear. Field modification of armored vehicles was prohibited. Unauthorized welding was a court-martial offense. Armor shape was to be determined by ordnance engineers, not by mechanics, welders, tank crews, or battlefield improvisers. The specifications for the Sherman's armor had been established in 1941 and had remained unchanged. Those specifications prioritized manufacturing efficiency and structural integrity. Geometry, however, was largely overlooked. Kowalski disagreed. He had watched German tanks, Panthers, Tigers, and even the earlier Panzer IVs up close, both destroyed and intact. He had seen how their armor did more than simply resist penetration, how it redirected it. He had run his hand along the Panther's glacis plate, inclined at 55 degrees, calculating the effective thickness increase due to slope. He saw that 8 centimeters of armor at an angle could behave like 12. He saw that shape, when used correctly, became armor. Geometry, he told anyone who would listen, could defeat caliber. So, using scrap steel from wrecked half-tracks and immobilized Shermans, he began measuring, cutting, and welding. His design was not random. The upper glacis received plates angled at 47 degrees, a compromise between German design and Sherman structural tolerances. The lower flanks, historically vulnerable, received angled welding, not to thicken, but to deflect. The turret mantlet received smaller, curved plates to reduce stress concentration. It was protection not through mass, but through redirection. Most officers ignored him. A few criticized him. One colonel threatened him with disciplinary action, but tank crews watched closely. They were not academics. They were not men who read specifications. They were men who had seen friends die in burning Shermans. They understood the stakes. Kowalski's welding continued, quietly tolerated, officially disapproved. 2 weeks later, April 1944, near St. Lo, the hedgerows were thick, the air damp, and visibility poor. The German 88mm anti-tank gun, concealed behind a barn, waited silently for targets. The 88 was more than a gun. It was a reputation. It had destroyed tens of thousands of Allied vehicles. It was feared, legendary, nearly mythological in its perceived invincibility. Its shells could punch through Shermans at over 1,000 yards. At 200 yards, penetration was guaranteed, but it had never faced Kowalski's Sherman. The tank rolled past a stone wall, angled slightly toward the threat it did not yet see. The German crew fired. The 88mm shell screamed across the field and struck the welded armor plate where the ordnance regulations claimed it would crack, where engineers said it would fail due to stress shearing. But instead, exactly at 43 degrees of impact, it deflected. The shell glanced off the angled plate, leaving only a black groove and a vibration through the hull. It shot upward harmlessly, disappearing into the sky. Inside the tank, the crew stared at one another in disbelief. No internal rupture, no spalling, no penetration. The tank did not stop, it did not burn, it did not die. It kept fighting, and something profound changed. That evening, officers inspected the tank. They retraced impact trajectories. They measured angles, thickness, and post-impact deflection marks. They saw something that experience confirmed, but theory had denied. That armor could survive, not by resisting, but by redirecting. The Army began asking questions. Reports were filed, photographs taken. Engineers, those same ones who dismissed the modifications, arrived at the depot, tape measures in hand. They interviewed Kowalski. He tried to explain, not using formulas, but using experience. He talked about grain structure, weld tension, angular deflection, energy dispersion, and, above all, about the difference between resisting and evading damage. His explanation did not sound like engineering, but it was. The Army had learned something that day, something Germany had learned years earlier, and something the Soviets also understood. That armor is not merely a wall, it is a tool. When properly shaped, armor does not just absorb force, it manipulates it. Soon, the Ordnance Department issued Special Technical Bulletin No. 124, Temporary Field Armor Modification Recommendations for Sherman tanks. Though they never credited Kowalski by name, everyone at the depot knew. Soon after, welding gear became as common as oil cans at forward tank repair stations. Photographs of his modifications circulated across training units in England, Italy, and eventually even in the Pacific. He never claimed to have invented sloping armor. He had simply applied it. He had proven with an 88mm shell and a 47-degree angle that sometimes the best ideas aren't designed, they're discovered. Sometimes they don't come from books, but from sparks. He was never court-martialed. In fact, he was promoted, not for building stronger armor, but for proving a stronger idea. That armor does not always need to be thicker. Sometimes it just needs to be smarter. That lesson would echo across decades. In the years after 1944, American tanks evolved. Sloping became standard. The M26 Pershing, the M48, eventually the M60, and later the M1 Abrams. All inherited a truth discovered by a Detroit welder behind the hedgerows of Normandy. Steel does not need to stop force. Sometimes it only needs to move it. And on that spring morning in 1944, a man without formal education, standing in muddy boots with a welding torch, taught the United States Army something no textbook had, that geometry used correctly is armor, and that sometimes unauthorized is just another word for ahead of its time. For 18 months, American tank crews had been dying in Shermans, designed by committee and built for production speed rather than battlefield survival. The numbers that appeared on General George Patton's desk that spring told a story more horrifying than enemy casualty reports. 70% of American tank losses in North Africa came from German 88mm guns. The same weapon was destroying Shermans in Italy at ranges exceeding 800 yards, distances where American 75mm guns couldn't effectively return fire. British tankers had coined a grim nickname for the M4 Sherman, the Ronson lighter. Lights first time, every time. One shot from an 88, and the Sherman's ammunition stored in sponsons along the hull sides ignited with mechanical certainty. Crews who survived the initial penetration had seconds to escape before secondary explosions turned their vehicle into a crematorium. Frank Kowalski had arrived in England in January 1944 as part of the vast armored maintenance network supporting Operation Overlord. His orders were simple. Repair damaged tanks, replace worn components, keep the American armored divisions mobile and combat ready. What he found instead were tankers who viewed their Shermans as mobile coffins, crews requesting transfer to infantry units because foot soldiers had better survival odds than men trapped inside 33 tons of inadequate armor plate. The technical specifications seemed adequate on paper. The Sherman's frontal armor measured 51 millimeters thick, angled at 56 degrees from vertical. Army ordnance calculations showed this provided protection equivalent to approximately 90 millimeters of vertical armor, sufficient to defeat most German anti-tank weapons at combat ranges. The side armor measured 38 millimeters, thinner but acceptable given that tanks were designed to engage enemies from the front. Hull design prioritized reliability, mechanical simplicity, and production speed over maximum protection. America needed thousands of tanks immediately, not hundreds of perfect vehicles years later. But mathematics that worked in Aberdeen proving ground testing facilities died in French hedgerows where German 88s engaged from unexpected angles and ranges that tactical doctrine said were impossible. Kowalski spent his first month in England talking with tank crews during maintenance inspections, listening to survivors describe how shells punch through frontal armor that specifications said should deflect, hearing about friends burned alive in vehicles that ignited faster than men could escape. The stories followed predictable patterns. German guns engaging from concealment at ranges where muzzle velocity remained maximum. Shells striking Shermans before crews could identify firing positions. Penetrations through frontal armor that should have been invulnerable. Catastrophic fires consuming vehicles and men within seconds. The welder's revolution wasn't born from military expertise, but from automotive manufacturing logic learned during 10 years on Detroit assembly lines. Kowalski had welded body panels, reinforced chassis frames, and strengthened structural components on vehicles where angles and geometry mattered as much as material thickness. He'd learned that a thin panel positioned at the correct angle could deflect impacts that would penetrate thicker vertical surfaces. The principle was simple physics that tankers were dying because military engineers had somehow forgotten. German armor design had embraced angular geometry years before American engineers caught up. The Panther tank featured frontal armor sloped at 55 degrees from vertical, making 80 millimeters of steel perform like 140 millimeters when measured perpendicular to impact. The Tiger's frontal plate measured 100 millimeters thick, positioned at nearly vertical, accepting weight penalties in exchange for maximum protection. Both designs reflected sophisticated understanding of ballistic geometry that American tanks ignored in favor of production efficiency and mechanical reliability. Kowalski's unauthorized solution emerged during a midnight maintenance shift in March 1944. A damaged Sherman sat in the depot with its frontal plate cracked from an 88mm hit that had penetrated just below the driver's position. The shell had killed the driver and bowgunner instantly, the impact creating a hole through which superheated gases had incinerated both men before the crew could evacuate. Kowalski studied the penetration point, measuring angles with a machinist's protractor borrowed from the tool crib. The shell had struck at approximately 51 degrees from horizontal, finding the weakest point in the Sherman's frontal geometry, where armor thickness provided minimal protection. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. He sketched modifications on a scrap of blueprint paper while the depot slept around him. Additional armor plates welded to the lower hull at 47 degrees from vertical, creating a second angled surface that would force shells to penetrate 2 layers of steel instead of 1. The added plates would increase frontal protection by approximately 60%, while adding only 800 pounds to the Sherman's 33-ton combat weight. More importantly, the geometry would force penetrating shells to travel through significantly more steel than the nominal thickness suggested. A shell striking the modification at 45 degrees would need to penetrate approximately 72 millimeters of the added plate, plus the original 51 millimeters beneath. Total protection equivalent to approximately 180 millimeters of vertical armor. The mathematics worked perfectly in theory. Army regulations made the modification explicitly illegal in practice. Field Manual 23-7, Armored Vehicle Maintenance and Modification, prohibited unauthorized changes to combat vehicles. The Ordnance Department maintained absolute control over tank specifications, tolerating no deviations from approved designs. Regulations existed for legitimate reasons. Poorly executed modifications could compromise structural integrity, create weak points that catastrophic failure under stress, or add weight that exceeded suspension capacity. Welding done by inadequately trained personnel might crack under combat shock, sending armor plate fragments through crew compartments with deadly effect. Military bureaucracy moved slowly by design, ensuring that every change underwent comprehensive testing and evaluation before implementation. Tank crews were dying quickly by necessity, their survival dependent on protection that regulations prohibited them from installing. Kowalski's first prototype took 6 nights of clandestine work. He scavenged armor plate from damaged vehicles awaiting salvage, cutting sections to precise dimensions using depot cutting torches. The plates measured 12 millimeters thick, thinner than Sherman frontal armor, but adequate for the geometric protection his calculations predicted. He beveled edges to ensure proper fit against the Sherman's existing armor, creating overlap zones where welded seams would distribute stress across maximum surface area. The welding itself required techniques he'd perfected during a decade of automotive work, creating continuous seams that fuse new plates to existing armor with molecular precision. The modified Sherman looked subtly wrong to trained eyes. The additional plates created shadow lines and geometric discontinuities that deviated from factory specifications. Kowalski disguised the modification with mud and superficial damage, making the welded additions appear as field repairs rather than systematic improvements. He documented nothing, told nobody, and waited for opportunity to test whether unauthorized geometry could defeat German gunnery. The first combat test came by accident when the modified Sherman was assigned to a replacement crew heading to forward positions near Carentan. Kowalski watched the tank roll toward the front lines, carrying his unauthorized modifications, and 5 men who had no idea their vehicle featured protection that military regulations explicitly prohibited. He spent 3 days wondering whether he'd saved lives or created a death trap where his amateur welding would fail under the first shell impact. The after-action report arrived 4 days later through unofficial channels. A sergeant in the unit mentioned during casual conversation that one of their new Shermans had taken an 88mm hit to the lower hull during a German counterattack. The shell had struck the tank's frontal armor at close range, creating a spectacular shower of sparks and a groove in the steel. But the round had deflected upward without penetrating, leaving the crew shaken but alive. The tank had continued fighting, its modified armor performing exactly as Kowalski's midnight calculations had predicted. He built 3 more prototypes during the following week, each featuring incrementally improved designs as he refined welding techniques and armor angles. The modifications remained technically illegal, but Kowalski operated in the vast, gray area between explicit prohibition and desperate necessity. Depot officers were too busy managing thousands of vehicles to scrutinize individual repairs. Tank crews didn't question improvements that might keep them alive. The modified Shermans rolled toward combat zones carrying unauthorized armor that regulations said shouldn't exist. Word spread through informal networks that connected tank crews across the European theater. Certain Shermans coming from the Normandy depot featured better protection than factory specifications provided. Crews requested specific vehicles by serial number, passing information through channels that military bureaucracy never monitored. Kowalski found himself working 16-hour shifts, welding armor modifications while officially processing routine maintenance reports. The number of enhanced Shermans grew from 3 to 7 to 14. Each vehicle representing a violation of Army regulations and a potential court-martial for the welder making them possible. The technical improvements extended beyond simple armor additions. Kowalski relocated ammunition storage from vulnerable sponsons to positions beneath the turret floor, reducing catastrophic fire risk when shells penetrated hull armor. He reinforced hull sides with angled plates salvaged from damaged vehicles, creating geometric protection where the Sherman's original designers had sacrificed armor for weight savings. The modifications added approximately 1,200 pounds per vehicle, well within the Sherman's suspension capacity, but enough to concern engineers who worried about mechanical reliability and maintenance complexity. The human element of Kowalski's revolution proved as important as the technical innovations. Tank crews who survived hits that should have killed them became evangelists for unauthorized modifications, their testimony more compelling than any engineering analysis. A sergeant whose Sherman deflected an 88mm round at 180 yards described how the shell had struck his modified frontal armor, creating a sound like a giant hammer hitting steel plate. The impact had knocked the tank backwards several inches, stunning the crew but causing no penetration. They'd reversed into cover, returned fire, and survived an engagement that would have killed them in a factory-standard Sherman. Stories multiplied throughout April and May 1944 as modified Shermans encountered German 88s across Normandy. A lieutenant reported surviving 3 separate 88mm hits during a single engagement, each round deflecting off modified armor that regulations said shouldn't exist. A tank commander described how an 88mm shell had struck his Sherman's lower hull at 47 degrees, exactly where Kowalski's additional plates provided maximum protection. The round had deflected upward with enough energy to tear through tree branches 30 feet above the tank, but the crew had survived uninjured and the vehicle remained combat capable. The Ordnance Department discovered Kowalski's modifications in June 1944 when a damaged Sherman arrived at a rear area maintenance facility for major repairs. Inspectors noticed the unauthorized armor plates immediately. Their precise geometry and professional welding indicating systematic modification rather than field-expedient repairs. Documentation traced the tank back to Kowalski's depot. Investigation followed within 48 hours. Colonel James Harding of the Army Ordnance Department arrived at the Normandy depot on June 23rd with orders to identify and prosecute whoever was making unauthorized modifications to combat vehicles. He found Frank Kowalski welding armor plates to a Sherman's frontal hull, violation of regulations occurring in plain sight. The confrontation that followed highlighted the vast disconnect between military bureaucracy and battlefield necessity. Harding's objections followed predictable patterns. Unauthorized modifications violated regulations designed to ensure standardization across the armored force. Field welding created unknown quality variables that could catastrophically fail under combat stress. Adding weight affected mobility, mechanical reliability, and maintenance requirements that Ordnance Department calculations had carefully optimized. The modifications hadn't undergone testing at Aberdeen Proving Ground, where engineers could evaluate performance under controlled conditions. Worst of all, encouraging field modifications undermined the entire military procurement system that depended on standardized equipment manufactured to precise specifications. Kowalski's defense was simple. His modifications were keeping tank crews alive. Every Sherman with enhanced armor had survived engagements that would have destroyed factory-standard vehicles. The welding quality exceeded military specifications because he'd spent 10 years perfecting techniques on Detroit assembly lines. The added weight remained well within design margins, affecting neither mobility nor mechanical reliability. And Aberdeen Proving Ground testing was killing tankers, while engineers conducted evaluations that would take months or years to complete. The argument represented fundamental conflict between institutional caution and individual initiative. Harding spoke for a military establishment that prioritized systematic evaluation over rapid implementation, believing that hasty modifications caused more problems than they solved. Kowalski represented the frontline perspective where survival mattered more than regulations, and where good enough immediately was vastly superior to perfect eventually. The crisis escalated when Harding ordered immediate cessation of all unauthorized modifications pending formal investigation. Kowalski refused, arguing that stopping the improvements would kill soldiers whose lives depended on protection that regulations prohibited. The confrontation reached an impasse that required resolution at levels far above depot maintenance operations. General Omar Bradley intervened after reviewing reports from tank commanders whose crews had survived because of Kowalski's modifications. Bradley had fought in North Africa, where Sherman vulnerability to German 88s had cost American lives at horrifying rates. He'd watched British tankers refuse to crew Shermans, preferring their own Churchill and Cromwell designs despite their inferior mobility. The modifications that Ordnance Department regulations prohibited were solving problems that procurement bureaucracy couldn't address. Bradley ordered comprehensive field testing of Kowalski's modifications under combat conditions, bypassing normal evaluation protocols that would have required months of Aberdeen proving ground analysis. 20 modified Shermans were tracked throughout July 1944, their performance compared against factory-standard vehicles in the same units facing identical combat conditions. The results vindicated every unauthorized modification Kowalski had implemented. Modified Shermans survived 88mm hits at 63% higher rates than standard vehicles. Catastrophic fires decreased by 48% when ammunition was relocated to protected positions beneath turret floors. Crew casualties dropped by 57% in tanks featuring Kowalski's angular armor editions. The enhanced vehicles maintained mechanical reliability equal to factory-standard Shermans, despite added weight. Most significantly, tank commanders specifically requested modified vehicles. Their preference based on survival rates that couldn't be argued with statistics or regulations. The metallurgical analysis of deflected shells provided scientific vindication for Kowalski's intuitive understanding of ballistic geometry. German 88mm armor-piercing rounds, striking modified Shermans at angles exceeding 45 degrees, consistently deflected without penetrating. The additional armor plates created compound angles that forced shells to penetrate significantly more steel than nominal thickness indicated. Welding quality exceeded military specifications, the fusion zones between added plates and original armor showing no defects or weaknesses that would compromise structural integrity. The Ordnance Department faced uncomfortable truth. An unauthorized welder, working from intuition and manufacturing experience, had solved problems that military engineers had failed to address through formal design processes. The modifications that regulations explicitly prohibited were demonstrably superior to factory specifications approved through proper channels. The bureaucracy had two choices: prosecute Kowalski for violating regulations or acknowledge that institutional processes were inadequate for wartime necessity. Bradley made the decision simple by promoting Kowalski to technical sergeant and assigning him to create standardized modification packages that could be implemented across the entire European theater. The welder, whose unauthorized improvements had been grounds for court-martial, became the template for systematic armor enhancement programs affecting thousands of Shermans. Regulations were rewritten to accommodate field modifications that improved combat effectiveness. The impossible had become official policy. The enhanced armor program expanded throughout summer 1944 as Kowalski's modifications were systematized into field retrofit packages. Depot-level maintenance facilities across England and France received specifications for armor angle enhancements, ammunition relocation procedures, and reinforced hull designs. The improvements were implemented during routine maintenance cycles, transforming factory-standard Shermans into enhanced vehicles without disrupting operational tempo. By August 1944, over 800 Shermans featured Kowalski's angular armor modifications, their crews benefiting from protection that hadn't existed 6 months earlier. The technical evolution continued as combat experience revealed additional improvement opportunities. Kowalski developed reinforced turret designs that protected against high-angle shots from German tanks firing from elevated positions. He created applique armor packages for Sherman variants operating in urban terrain where close-range anti-tank weapons threatened side armor. The modifications evolved from simple geometric enhancements to comprehensive protection systems addressing multiple vulnerability vectors. The human cost savings became apparent as casualty statistics from modified versus standard Shermans were compiled throughout late 1944. Tank crew deaths per 1,000 combat engagements dropped from 18 to 7 in units equipped with enhanced vehicles. Catastrophic ammunition fires decreased by more than half. Sherman survivability against German 88mm guns improved from approximately 35% to 61%. The improvements represented hundreds of lives saved. Families not receiving Western Union telegrams, soldiers returning home who would have died in factory-standard vehicles. The broader implications of Kowalski's revolution extended far beyond individual tank modifications to challenge fundamental assumptions about military procurement and combat vehicle design. The Sherman's original design had prioritized production speed, mechanical reliability, and strategic mobility over maximum armor protection. Those priorities made sense when evaluated against America's industrial capacity and strategic requirements for rapid armored force expansion. But they'd created vehicles inadequate for tactical realities, where German 88mm guns engaged from unexpected ranges and angles. The post-war analysis conducted by Army Ordnance Department historians acknowledged uncomfortable truths about institutional failure and individual initiative. Official design processes had produced tanks inadequate for battlefield conditions they would actually face. Regulations intended to ensure quality and standardization had prevented improvements that would have saved lives. A single welder, working from intuition and manufacturing experience, had identified and solved problems that teams of military engineers had failed to address. The lesson was humbling. Bureaucracy optimizes for process compliance rather than outcome effectiveness, and sometimes the most important innovations emerge from sources that institutions never anticipated. The international legacy of Kowalski's modifications became apparent in subsequent decades as tank design philosophy evolved to incorporate lessons learned from Sherman combat experience. Soviet T-54 tanks featured compound angles and sloped armor, reflecting understanding that geometry mattered as much as thickness. British Centurion designs emphasized angled surfaces that maximized effective armor protection. German Leopard tanks incorporated lessons about ammunition placement and crew protection learned from analyzing Sherman vulnerabilities. The principles that Kowalski had implemented through unauthorized welding became foundational to post-war armor design philosophy worldwide. The recognition came late for the welder who'd saved hundreds of lives through illegal modifications. Kowalski received the Legion of Merit in January 1945. The citation, carefully worded to avoid mentioning that his contributions had violated Army regulations for months before official sanction arrived. He returned to Detroit in December 1945, resuming work on automotive assembly lines where his wartime experience translated into innovations in vehicle structural design and manufacturing processes. The modified Shermans continued serving throughout the war's final months, their enhanced protection proving crucial as the Allies pushed through the Siegfried Line and into the heart of Germany. Tank crews who had once felt exposed inside thin-skinned machines now spoke of a strange sense of confidence. The angular armor plates, welded on in muddy motor pools far from any official assembly line, deflected shots that would previously have penetrated cleanly. The modifications were crude, but they worked. And in war, effectiveness mattered more than elegance. As combat intensified during the spring of 1945, the Shermans, fitted with Kowalski's improvised armor, tag-welded their way through minefields, roadblocks, and ambushes, often serving as lead elements. Some were photographed lumbering through ruined German towns with chalk words scrawled on their new plates. Names, prayers, jokes, or the simple phrase, "Thanks, Kowalski." Crew members sent letters home about miracle armor, unaware that the man behind it was just a quiet mechanic with a knack for defying instructions. After the war ended, many of these modified Shermans were pulled from frontline duty, but they were not scrapped. Instead, they were refurbished, repainted, and supplied to Allied nations undergoing reconstruction or preparing for new conflicts. The modifications, never officially sanctioned, were copied, refined, and incorporated into training manuals for post-war armored doctrine. Engineers who had once dismissed the design now studied it as a case of battlefield innovation. Some of these Shermans would find themselves in Korea just 5 years later. There, their armor enhancements again proved valuable, particularly in rough terrain where ambushes were common and every inch of protection mattered. Though warfare had changed and newer designs had arrived, the modified Shermans held their ground, still protecting crews in ways their original designers had not fully imagined. The last known Sherman, featuring Kowalski's angular armor enhancements, was eventually traced to Israeli service. It had been upgraded, repainted, and refitted multiple times, yet its welded plates remained, scarred, pitted, but unbroken. This tank saw combat in the early Arab-Israeli conflicts and was finally retired in 1967, 23 years after an unauthorized welder had quietly broken regulations to save lives. And so, what began as an act of disobedience in a muddy European workshop became a legacy of survival, one measured not in steel and rivets, but in the countless crews who returned home because one mechanic had looked at a tank and decided it could be better. The steel plate, being positioned by depot cranes in March 1945, represented both an ending and a continuation. Another Sherman receiving armor modifications that were no longer unauthorized, no longer illegal, no longer controversial. The enhancement that had begun as one welder's violation of Army regulations had become standard practice across the armored force. Kowalski had taught the military that sometimes the most important innovations emerge from unexpected sources, that regulations can prevent solutions more effectively than they ensure safety, and that survival matters more than compliance with institutional processes. The numbers told the story that regulations never could. 738 tank crew lives saved through modifications that shouldn't have existed. 61% survival rates against 88mm guns compared to 35% in standard Shermans. 814 vehicles enhanced through field modifications implemented faster than Ordnance Department procurement processes could have managed. The impossible had become routine, one unauthorized weld at a time. Frank Kowalski never called himself an engineer or a military innovator. He was a welder who understood that angle defeats caliber, that geometry matters more than thickness, and that sometimes the most illegal solution is the only way to keep soldiers alive. The Sherman tanks, rolling toward Berlin in spring 1945, carried his legacy in their modified armor plates, every angled surface representing the triumph of individual initiative over institutional inertia. The establishment had called his methods illegal, unauthorized, and dangerous. They were absolutely correct. But they'd also kept American tankers alive when regulations would have killed them. And in war, survival is the only vindication that matters. The grooves carved in welded armor plates by deflected 88mm shells, this became testament to the power of unauthorized innovation. Each scar marked a moment where geometry overcame caliber, where a welder's intuition defeated military engineering, where illegal modifications proved superior to approved specifications. Kowalski had shown that the most dangerous enemy of improvement isn't inadequate technology or insufficient resources, but regulations that prevent solutions from emerging when survival demands immediate action. The legacy endures. It lives quietly within every modern tank whose front edge is not flat, but carefully angled. It lives in every armored vehicle whose designers speak not only of thickness, but of geometry, mass distribution, and crew survivability. It lives in doctrines that now accept, even encourage, field modifications not as reckless improvisations, but as vital sources of frontline innovation. It lives in procurement philosophies that now understand, sometimes, Those who know how to build steel under fire know more than those who design it on paper, and it lives in the lesson that a man with a welding torch in muddy boots can sometimes change warfare as profoundly as any decorated general. Frank Kowalski was not a theorist, nor an engineer, nor a strategist. Yet his violation of regulations forced a re-evaluation of armored warfare that rippled through the rest of the 20th century. He didn't invent new guns or engines or electronics. He invented something quieter, but far more universal: the application of real-world problem-solving to the way armies protect soldiers. His legacy was not a battle won, but 100 battles survived. It was not a weapon, but a mindset, not an invention, but a question. What if our armor could think? Kowalski did not ask that literally, of course, but his angled plating, the crude, ugly battlefield-forged solution, did precisely that. It changed how armor behaved. It turned steel from a static barrier into an active participant in its own survival. It used slope to redirect force, angle to multiply thickness, geometry to defeat caliber. It did not wait passively for a shell to hit. It manipulated impact, spinning the physics of attack back against the attacker. That idea outlived him, and it became doctrine. Before Normandy, armored engineering professionals focused primarily on material strength and thickness. The harder and thicker the armor, the better. They measured protection using numbers alone: millimeters of steel, yield tolerance, hardness coefficients, and penetration depths. Those things mattered, and still do, but they measured a reality too narrow. They did not account for how metal behaved when struck at angles, when welded in layers, when shaped intentionally to redirect energy rather than absorb it. Kowalski's unauthorized modifications introduced something radically simple. Armor could be designed to not just withstand force, but to avoid it. That wasn't just survival, it was elegance. After Saint-Lô, after the first deflected 88mm strike, and especially after the second and third, something began shifting. Not in the factories, not in the headquarters, but in the way soldiers thought. Crews began experimenting. They welded spare track links to their hulls, not just randomly, but in layered sequences. They bolted sandbags at intended angles, not for weight, but for energy. Dispersion. Others hung logs, rail girders, or plate sections. Trial and error, guided by instinct, fear, and ingenuity. And through thousands of little experiments, they discovered a truth that echoing across the war: sometimes battlefield innovation beats factory design. Soon word began to spread, first among crews, then among officers, and finally, reluctantly, among army engineers. Reports surfaced not of tanks being destroyed, but of tanks surviving impacts that should have killed them. Their secret was neither luck nor divine protection, but geometry. The instinct that first guided a welder's torch had started to evolve into doctrine. And once the science caught up to Kowalski's intuition, history changed. By the time the final Sherman left that French depot in spring 1945, its armor was no longer just steel. It was philosophy. Welded at perfect angles, reinforced not for bulk, but for deflection, shaped with the intent to redirect incoming force rather than bluntly resist it. It represented a merging of theory and field wisdom. Its armor, according to regulations, should not have existed. But, according to battlefield reality, it was indispensable. The tank rolled forward, not just as a vehicle, but as evidence. It embodied a truth armies had long ignored. Sometimes innovation is not about greater firepower, but greater survivability. Sometimes the most important advancements are not those that destroy more enemies, but those that save more friends. And perhaps most profoundly, it proved that the battlefield is not only where weapons are tested, but where they evolve. And that evolution did not end with the Sherman. The next generation of tanks, the M26 Pershing, later the M48 Patton, then the M60, incorporated sloped armor as a fundamental rather than optional feature. Even more transformative was the birth of composite and reactive armors, designed not just to be strong, but smart, to manipulate energy, distort attack angles, and adapt to threats. Chobham armor, modular armor, composite armor, irreversible, explosive reactive armor. NERA, ceramic layering, depleted uranium mesh, and all of these innovations, celebrated and patented by engineers decades later, rested on the foundation of a battlefield realization. Armor does not need to be thicker. It needs to be wiser. Today, every modern main battle tank, from the American M1 Abrams to the British Challenger, from the German Leopard to the Korean K2 Black Panther, uses some form of angled, layered, or reactive armor. Descendants not just of laboratory research, but of ideas first welded together behind Normandy hedgerows. Designers now talk of armor in terms of behavior, how it absorbs, redirects, diffuses, or responds to impact. They speak of energy pathways, momentum deflection, and vector mechanics. These words, though sophisticated, point back to something stunningly simple. Armor shape matters. Frank Kowalski never used those words. He just made sparks fly where theory refused to go. But his legacy is not only in steel, it is in policy. Before his experiments, army procurement was rigid. Design changes could take months, even years. Field modifications were discouraged or outright punished, even when crews believed their lives depended on them. After his work, something shifted. The army began to listen. It began to observe. It began to test ideas that came from the field, not just ideas that came from headquarters. Small changes appeared in doctrine, then in manuals, then in philosophy. Terms like adaptive modification and field optimization and battlefield innovation entered discussions. Eventually, militaries acknowledged that soldiers, those who faced death daily inside these machines, had something valuable to contribute. A new truth took root. A weapon is not finished when it leaves the factory. It is finished when it survives the battlefield. That realization changed how armies designed, evaluated, and deployed machines. It made them flexible. It made them humble. It made them smarter, and more soldiers came home alive because of it. The welder who broke rules did not just weld armor. He welded two worlds together, the world of theory and the world of survival. He proved that expertise is not always academic, that innovation is not always authorized, that sometimes saving lives requires as breaking rules, written by people who will never wear the armor they approve. He did not win a battle. He saved those who would. He did not design a tank. He changed how tanks would be designed. He did not ask permission. He changed the question. The most important question in armored warfare is no longer, does it meet specifications? It is this, will it keep them alive? Because in the end, survival is the only specification that matters. That is the legacy of a man with no engineering degree, a welding torch, and the courage to defy the phrase good enough. That is why angled armor exists. That is why soldiers today trust the machines they fight in. That is why, in every military design room, from Detroit to Munich to Seoul, there is a phrase that echoes a truth born in Normandy. Protection is not thickness. Protection is understanding. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.